PostGis is complicated, and so there's a lot to learn about working with maps and GIS. I'm going to give a quick highlight through some of those topics that are really independent of technology. They're more about what does it mean to have a map. So, background on Pow Pow. Pow Pow, you can call it AI for farming. You can call it applied irrigation control, because that's what we're currently working on. We're partially funded by a California state grant, which is all about helping farmers be more efficient. And we take in data. We're a software company. We are doing hardware. So we take in data from a variety of data partners, do the crunching and so forth, to deliver both alerts, when is their problem, what do they need to do, and maps showing them how to make decisions. So a lot of things where one drawer put it very nicely, whatever I do, I'm going to have a problem. So pick which problems I'm going to have. And help me make that decision. Give me the right data at the right time to make that decision. That's what we focus on. And because we're looking at making decisions, there's a lot of uncertainty of how does it show up on a map. So here we have a map that has three different kinds of things. It has our pumps, there are wells, a lot of California farms use irrigation. And you can see that we have yellow. We've marked this one as that well as having a problem. We also show sort of how the plants are doing based on airplanes flying over. We give that imagery. Again, it's all presented on a map. So to do that, you need to have a geographic information system underneath. So just like you need to learn a little bit about database, I'll give you a little bit about maps. They're built out of layers that represent something. So you have the real world, which is a whole lot of stuff. And then you might have what's called raster data, you can think of as pixels. But they are flat. They're not on the contour of the hill. And the value can mean any of a lot of different things. Plant figure, elevation, and so forth. Or vector layer, which is locations. So here's a vector layer. You can have polygons, these are cities in a part of Massachusetts, and lines. Raster data, I already talked about, rectangular cells. It's interesting that they're often not square. And there's interesting issues around taking from an airplane, taking a picture of a hillside. Because not only are they not square, they change as you go up the hill. Because it's square pixels of airplane, but it ain't on the ground. An important part of bringing in the data is what kind of data comes with it. So, what do you get that goes with it? So in a vector layer, which is what we'll be talking about later, you bring in additional columns of data. And you can think about that additional data as the attributes that help you understand the data or make sense out of the data. So it's not just a polygon, it's a polygon with a name, an acreage or a crop, whatever the right thing is. In this example here, it's the population for the state. The other unfortunate things about maps is that their world's not flat. It's not even a sphere. It's an ellipsoid. And so what you think of as latitude, longitude is the location on the ellipsoid. But screens are flat. So maps are flat. And so there's this projection. So there's always some distortion depending on how much and for what purpose. And I show here 4 different projections commonly used for the United States. And all of them are wrong in some way. It's a question of by what metrics do you want to look at. So we move on to thinking about how do you do all that in software. So we're like Django here. So, we've been building this Django application for about 5 years. So it's Django on the server side. We use the GIS algorithms that come with GeoDjango, but they're important to know because at some point you end up having to deal with the actual geometry algorithms. Those are done through GDAL and OGL. There's a lot of little fussy bits that's like, well, GeoDjango kind of helps, but I need to really deal with the details. It's just, you see the same thing when you go to machine learning talks or AI talks where they say, well, you need to do this other stuff, and well, that's not the intensive for you, do that some other place. This is the kind of other place for GIS data. And of course, PostGis is how you store the data in database. Because there is a lot of data, it's oftentimes convenient to use the external tools that aren't Django. And we were fortunate in having a geographer work for us that helped train the team on a bunch of these. As he said, a 2-year program in geography at a master's degree at University of California, Santa Barbara, you learn a lot. And he tried to teach us a little bit in the year that he was with us. So when you're working through a GIS application, or really any mapping application, and machine learning is kind of similar in some ways, you have to start with what's my data? Where do I get my data? And that's always in itself its own journey and process across the company. That's not necessarily a developer task. It's often done by product managers, but it's an important thing because the developers end up having to say, well, the data has these problems. What are we going to do about it? Do we go back and get the vendor to fix it? So we just did that with one of our vendors. Can we cope? And just get reduced accuracy results. Then you got to do clean and import. And if you've been in any machine learning talks, they talk about this same problem. How do you clean the data? How do you make the data make sense? The stuff we do for the GIS stuff, oftentimes that means like removing points, combining duplicate points, smoothing the corners, because like the data I'll show later is generated by some piece of software, and it will put points 1 foot apart. Well, I don't really need that in my database. I can kind of simplify that. And then you're going to pre-compute the data, and then we'll walk through the Django parts here, which is how to fetch the data and get it back up to the web browser. So I'll walk through this in the context of a specific example that we're actually still in the process of, which is showing the California shape data. This is a pretty big font. It needs to be usable on the website. You want it to be fast enough to make sense to people. You don't want it to take a minute to load. This is an example of what it looks like. So we start with this data file, and it came from the California Department of Water Resources, which is why it's 2014. They purchased it from somebody, but they're making it available for relatively low cost. And we are partially funded by the Energy Commission. But it's a lot of data. I mean, 400,000 rows, 400 megabytes on a disk. So it's a pretty good sized data set. It's not giant by any means, but it's also not so small you're going to look through it all. You got to write programs to handle it. So we had to deal with this cleaning issues, and that in and of itself took a day or two to figure out how to turn it into useful data. Now we have a model. In the databases, I'll just cover the quick bits here around how you work it in Django. The Django GeoDatabase, GeoDjango has a nice tutorial. So that walks through the basic process. This isn't that different here. You've got a polygon field. What's different is we're using it in a specific projection, which is a California-specific projection that many state agencies use. And so we said, okay, fine, keep it that way, because when we get other data from state agencies, we want it to be identical. Because if you transform it and then transform it back, you don't actually always get the same answer. You kind of don't want to do that if you don't have to. One of the things that Django does nicely is it created the index format. If you read about GIS systems in general, making sure you have the right index is always a tricky question, particularly on larger data sets. So now, walking back through that little flow diagram, you say, well, I want to compute the data for display. It's pretty straightforward. You have to transform the data out of the database into the right coordinate system, and then we get to round it. This is important because the the Django REST framework, and pretty much everybody, all other REST frameworks, will by default give you like 14 digits. Well, I'm sorry, Earth coordinates, 6 digits is just fine. 120, 122 minus 122 degree latitude with 6 more digits gives you 1 foot resolution in California. You don't need 10 digits. So that makes that rounding of it makes the data you gotta send to the browser about half size. So you're gonna send hundreds of thousands of these at a time, it matters. But the transformation and the rounding process is pretty slow. So we don't really want to do that as part of each call. It's very easy to have a call that will return 125 shapes, 500 shapes. We kind of do it so they don't try to return too many more than that. But you don't want to take 3/10 of a second just in this part, not counting the part, sending it over the wire or displaying it on the road. So we end up pre-computing that and storing it in the database. It took quite a while. I mean, a lot of these polygons have a lot of points. They're polygons with 100 or 200 points. So we store those strings in a database so we don't need to do it again. When we're rendering, we can just pull it out of the database, give it to the web browser. The second problem you have is there's a lot of shapes. As I said, it's 300,000 shapes for the state of California. How do you deal with this? Well, it's a Django REST API based on what's in view. Fairly straightforward concept. Take what the map tells you in terms of what's being displayed, go ask for it. But the data we have actually has a lot of very small data sets. There's a lot of pieces of cropland that are somebody's backyard. It includes a lot of things that are parks. And it's like, yeah, we're not going to show that. We're dealing with farms. So there's a certain minimum size. And if you're doing too big on the map, well, you don't want to show anything. Because we have a notion called a ranch, which is what how customers organize their data. You just want to show the ranches if it's too big. So we create this object data in view that summarizes what we're telling the map and browser to display. Now, to actually get those shapes is straightforward. You take the polygon, turn it into the right coordinate system, and do this intersection. That's the Django query that uses a particular PostGis function. It uses the index I mentioned. Now, the reason why I say check performance is a friend of mine works at Streetlight Data. As I said, this data set's 400 megabytes. Their data set's 4 terabytes, 10 times as big. They pay a lot of attention to this story performance. And their machine learning side has 400 terabytes of data. They do that offline. They don't do that in response to your questions. The other thing we do here is we use the Django queries feature, our values feature. There's something that I really like about Django. I came from a Java environment with Hibernate. It didn't have that. And it was kind of annoying. Because here it's like, well, I only need those 3 columns. I don't need the other 10 columns that are in the database. So I can just return that data, and it's immediately as a dictionary straight to give to whatever I need to do. So this is how it ends up looking like in the Django REST framework. We take the object that comes from this set of queries, which is the blocks, the customer shapes, the crop shapes, which is what we've been talking about, the equipment, pumps and solar installations and so forth, and we serialize it. And the trop shapes, again, is very straightforward. There's one of the things I really like about the Django REST framework is the database gave us a list of strings, a list of dictionaries. Well, we'd saved them as already as strings, so we just have a list of strings. It's just a simple JSON field. The blocks, the customer shapes, for this need, we only need these 4 columns. We don't need the other 25 columns in that database, some of which are pretty big. And there's a properties column unique shape that it could easily be several thousand bytes all by itself. But we don't need it for the maps, and we're not going to bring it over from the database. One of the things that, as she was saying earlier, Django Ref Framework is really sort of best in class. The last piece is actually showing it in the browser. I'm not going to talk too much about this because it's not the JavaScript thing. But the important thing to realize is that you've got to debounce the calls. There's a call on every mouse move. And then each of the different kinds of things has its own layer. So they can draw and manage whatever we want on that layer. So like, because I was showing the pumps have a color that comes with it, the status code. The crops are drawn in one color, the customer blocks are drawn in a different color, and so forth. And from a performance side, it's important for the JavaScript to be careful to only change the things it needs to change. I mean, it seems pretty obvious, but the first implementation didn't do that. And it was you could tell. Screen disappears, map reappears. Object disappears, object reappears. So, yeah, not a very pleasant experience. So we've talked through sort of this general flow here, in terms of what's needed and how the stuff works, and what it all gives us. And we're hiring. As she was saying, we're starting, we're hiring. We do have a sales office out in Fresno. If people want to work there, it's great because you actually get to meet more customers. In the main office, customers are never there. Customers are out in Central Valley. Questions before I go to the demo? Then I'll give a little demo. Yes?
Does your data pipeline also use Django, or is that just a completely different stack?
It's all over the map. Yeah, the inventory pipelines in C++, we do image processing, the machine learning for detecting problems, things are turning yellow, that's done in Python. The GIS processing is done with this variety of tools, primarily manually right now, because we're not, either we automate it, which we do in Python, or we're doing it manually to figure out what we need to automate. And one of the nice things, the reason why I mentioned the GDAL library, is the QGIS open source user interface. Every function in that user interface is in the GDAL library and callable from Python. So the stuff that I did to clean this data up, I mean, I have a set of notes. If we gotta start doing that every month, or even every year, we might say, oh, here's this list that I wrote down of 15 steps. Maybe we build a little Python script that does it. Because it's the same function. It's just instead of calling it this, you call it that, kind of thing. Other questions? Let me just go over. So this is an example of what the application looks like. So, oops, one mistake. How do I get this? No. You see that? Okay. So this is Pow Pow. As I said, we do generate alerts on pumps. Our first product was our pump monitor product. Yeah, these are, you can see the pumps out of the many hundred that are in our system, how many actually have a problem right now. This is our, when you talk about administrative dashboards, this is part of our administrative dashboard, to look at what is all the data from all of the customers. You can see we've got customers all over California. So I did I'm on my personal Wi-Fi here, so it's a little slow. I don't have the house Wi-Fi link. Make sure that's working. Yes. And then when you zoom in, you'll see here, you see how quickly that loaded. That's the reason why we do these kind of optimization. The projector doesn't show it quite well here, but these brown ones are the farm data we just imported. The white ones are a particular customer, and again, you can see it's pumped their pumps. And so I said there's this whole question around sort of optimizing display. So if you drag sideways, it pulls in the extra data to show it on one side. You begin to zoom out. You zoom out, we leave the customer data because that's important for an administrative side, but the farm shapes, now there's too many of them. There's no point in showing them. I mean, I actually did in my first version, and it would take, noticeable time, half a second or so, just to render it in the browser. I mean, nothing to do with server. There's just that much stuff. Google Maps is not, and JavaScript not super fast on that kind of thing.
Excuse me.
Excuse
I have a question.
Yeah.
You mentioned that you dispatch requests from JavaScript side to fetch different layers. For
Yeah.
example, on this map, what will be the different layers?
So right here, we're not using GraphQL. It's a macro, GraphQL, we might get there someday, but we're not there right now. We make a simple REST query that says, give me the map data for what's in view. And the map data right now has 5 kinds of things. It has the farm layer, which is the arrow shapes, that's what's new. It has the customer fields, which are white, the pumps. It has solar installations, which aren't drawn right now because there's a bug and I just turned it off. and buildings that they've put in. So we already have all of those layers. There's also a layer around sensor data, that what sensors have they put in the field, so that we can actually understand what's really there. And all that's handled, the server side splits it up, the maps in view sort of collects it all, does all those queries, collects the data, creates one payload to the client, and then the JavaScript, the jQuery code, splits it up again by layer to handle. And again, it's the kind of thing you might do in GraphQL in a different environment. We built it with jQuery and REST framework. Other questions? Yeah.
Are the subdivisions such that you get each plot of land or whatever, however you want to split it, are they limited to certain types of shapes, or is it any arbitrary polygon?
Well, you're asking about what's the limitation in our system, or what's GIS doing in general?
I guess let's keep it with the system that you guys have built. Is that, just within that?
We currently don't allow putting holes. And that comes up with some people that have like a reservoir in the middle of their field. Right? And so that's something, a limitation. It's not of the tools. It's merely of the user interface. And it's a little bit on the back end around how to deal with holes. So what we've done is we've worked around it. Because usually when there's a reservoir, there's a little road. And so you end up drawing this complicated shape that kind of goes up and around with a little road and then goes back out again. And what's really nice is the farm shapes that we import also do that in many places. So it was very nice that they did that. The company that built that data. So.
I have a very basic mapping question. It's very general. If I went about storing coordinates in a Django model, I might just make 2 float type fields. What do I get using PostGis and other libraries?
The big thing you get is indexing that is really spatially aware. And so to repeat the question, why use the GeoDjango functions and that kind of thing rather than just a simple logic? So We go back up to this slide. When I talk here about intersects, well, that's very simple here because I'm giving it a box, maybe a square or rectangle. But that's actually a very complicated GIS query because it says, now I need to go look at my data and figure out what's inside or outside or cuts through it. So when I have a polygon, well, it needs to say, well, okay, part of it's inside, part of it's outside. So that intersect is itself a fairly slow operation, which is why my buddies did it with 4 terabytes of data. They don't do it with this simplified, they do something more complicated. But for PostGis and for most people, it will be fine. Most people aren't going to get to 4 terabytes of data. The other thing that's nice about just not storing just plain latitude or longitude is that if you store it as a real object, you know, a polygon object or a line string object or geometry in PostGis, you can tell QGIS, which is the open source mapping tool, to read it and display it from the map from the database directly. So you can separate out, okay, is it my user interface that's busted, or is the data database wrong? And that's very helpful sometimes, because, you know, it's easy to get the data wrong, and then you don't really know this in the database, because then all the numbers look okay. But when you're out on a map, you realize, oh, it's just wrong. And you got to try to figure out where is it wrong, how to get that one. Other questions? Yes.
Do you deal with elevation at all in your data?
We have in research projects. We haven't done it in the product yet. I mean, we're dealing primarily right now with Central California, which is pretty flat. We have done research projects for people that are on the hillsides around Central Valley. And it is in our long-term plans to be more elevation aware. The problem with elevation is that now you've got to figure out sort of how do you make sense out of it. So we're talking with one of the resource conservation districts, for the people that help try to manage environmental water needs versus urban versus agricultural water needs. Here down in Santa Barbara, where elevation is a big deal. And they constantly fight this battle with everybody that wants to deal with, it looks like this on the map, but it's a hillside. The map doesn't show it to you. So there's a basic problem with how do you show the data in a way that makes sense when you start really having hillsides. And it's just, nobody has virtual reality yet for doing that. I mean, they do the first part. Nobody practical, but I know.
Thank you, Stan.